introduction. Please take a seat.
Oh, dude, that's really cool. Wait, is that? Oh yeah, you have your own email. They have their own email server. What do you use? I want some. So use Gandhi. MX. What is that? MX?
Is this seat okay if I sit there?
Do you now move the chair?
Oh yeah, so try it out a bit. No worries. Maybe I'll stand toward
Wait, so what? The service name is called Gandhi? What's the rate you have to pay for keeping the keeping the Oh, damn, Gandhi. Oh, sweet.
Hello, everyone.
Hello.
Thank you, Kevin. Thanks for coming today for the Graduate class. And Amy, I'm your host tonight. I was a developer before, and I did organize a Rust conference in China in April. And now I see since last year, I saw more and more blockchain projects to use Rust. So I started Rust in Blockchain newsletter monthly. Then you can check Rust in blockchain.org to check the updates. And this is our first meetup in San Francisco, and I'm so excited to be here. Thanks for Nervos team to make the event happen, and thanks for John Sonona for providing us so nice place. Let's start with our first speaker, Brian Anderson. You must already know him a lot. And he is a core team, Rust core team before, and he compounded the Rust programming language, and his sister project, Servo Browser Angie. And let's start with Ryan.
So these are my 2 drinks here, and you'll probably be able to tell like how well I think I'm doing by which one I'm drinking. Thank you, Amy. I'm very happy to be here. Talk about 2 of my favorite things, and also this kind of thing that is happening around the language. Amy. And she has this newfound passion for kind of being these Rust blockchain projects, one greater community, and figuring out how to better make the Rust community. And this is something that means a lot. So when she said she was very happy, I personally hate giving talks. Also, she just basically alright, so this is me. Thanks for bringing my beer closer. To tell you a little bit about my bona fides. Kind of in private, I tell people that I'm a Rust guru, and I mean that in the most cynical way possible. Because I know a lot about Rust, but I'm really, really good at making people believe that I know everything about Rust. And so people seem to really appreciate my opinion. And as a result, I've met a lot of people in the Rust communities, and especially in the Rust blockchain communities. I have learned to talk for minutes and hours on end about any Rust prompt you can give me. Now, whether I can do that right in front of all of these people staring at me, I have no idea. But we're going to find out. So all I have to say is I'm not a Rust blockchain expert. I'm a Rust expert. I'm a Rust blockchain cheerleader. But as for myself, I have a lot of experience with Rust. I worked at Mozilla on Rust from the very beginning. There's basically not a lot of people, there's this many people in the world that have more Rust experience than I do, which is something I'm pretty proud of. I don't know. So this is going to be a soft talk since I'm not a blockchain expert, but we have other talks after this that are going to be more detailed technical talks. And I don't really have a sense of what you're here for, whether you're Rust people or you're blockchain people, but I hope you're a mix of both. And I hope that this sort of like overview of the Rust blockchain world will at least have something for everybody. So as I said, like I've known a lot of blockchain projects, and I have been enthusiastically supportive of a lot of blockchain projects, but I'm not involved in any of them myself. And so this talk is going to be kind of like an overview about Rust and got into doing this talk is because a couple months ago, I suddenly met a whole bunch of new Rust blockchain companies. And once again, it hit me like how important the blockchain domain is for Rust success. And I think this is something that possibly not a lot of Rust developers have, and they would appreciate it more. But I'm feeling kind of an urge, sort of like Amy is, to raise the, elevate the awareness of how important the blockchain domain is to the success of Rust. And as I was writing this blog post, which corresponds to this, and I will give you a link afterwards, the news about Libra started trending. And I was like, oh my God, this is like the big one. If you don't know Libra, it's the big currency. And it's kind of like the biggest deal that's happened in a long time because it's people, everybody knows about it, your mom knows about Libra. And so I was like, I'm going to get this blog post done just in time to capitalize on Libra. And of course I didn't do that because I'm super lazy. But here we are now. So as I said, my audience is not necessarily a technical blockchain audience. My audience seems to be a Rust audience. So a lot of what I'm going to say is sort of advocating the amazing blockchain successes and non-blockchain successes, especially in the community, to a Rust audience, in hopes that there will be a growing appreciation there among the communities between these two somewhat disparate communities will start to come together and appreciate each other more. And I have about 20 to 30 minutes for this talk, and I haven't practiced this. I've thrown together information, a sense of where the speakers are and the feedback zones are. So I hope this is going to be pretty extemporaneous. And those of you might know a lot of these anecdotes that I'm going to give, and if you sense that I'm kind of rambling like I do, nudge me in one direction or another, or, whatever. But for this talk, the primary goal was to sort of like pull together all of the info out there about what's going on in blockchain related and sort of bring it in one place and bring it out. And while I was doing it, I was just shocked, because I already knew a lot about the people that are using blockchain and what they were doing, what they're doing. But there's so much more than I even thought. It's crazy. And I can't touch on all of it tonight. In the slide. But after the very you're going to see a link, and that link is going to everything you possibly want about Rust and blockchain. On the slide themselves, links, not a lot of text. I don't want you thinking too hard. I don't want you on your laptops and stuff like that. I just want to all the cool things that are going on. All the technical details, you can follow the links, and we'll get to them later. And I know because one of the best things that I've got going for a lot of stories about. I got stories. Talk a little bit so popular for blockchain. I think that's kind of it. That's something I hear people like, why you blockchain? I will tell you. That's all the rest. The thing that interests me more is what is so special about Rust speaking. So I'm going to talk more about that side. So that's I want to do it because Rust is sort of struggle with, and who cares about this piece of software. When Rust started, it was basically a toy project. And at Mozilla, where I didn't work yet, but where I was going to work soon, Brendan Ike, who was in the CTO, said, like, and I know you think favorite thing. Really freaking much. To, in my mind, like, what I do is like not really engineering. It's like throwing things at the wall and hoping, eventually they will turn something that my boss is like. But aerospace engineering, I think of as something that like you got to try hard at, and you need software that actually works and is reliable. So my personal dream is like, governments to do data. Trust is something we're putting in your anybody else on that team really shared that dream. That's like, to me, the pinnacle of reliable software. At the same time, though, there was like this blockchain thing was going on. Real evolution. It started, publicly before Rust did. But while we were developing Rust, Bitcoin was also developing. And for a long time, the cryptocurrency thing was really on our minds. It was kind of a slow burn cryptocurrency. Like for a lot of time, it was kind of a joke, and then it was a big speculative thing, and like always been a bit of like about whether cryptocurrency and blockchain technology is a real thing, if it's cool or if it's not cool. And I don't remember the exact moment when I realized, like, holy shit! Like, I'm sorry, I'm swearing so much. I might be nervous. But I'm gonna take another beer right now. And that's probably not gonna help. Alright, I will use the microphone closer to my mouth. I just keep hearing my voice. Yeah, I don't remember exactly when it was that I personally realized that like something was happening with the blockchain domain in relation to Rust. Certainly there were a few build projects. For a long time, we had no production users of Rust. Anytime there was any word out in the air, like if somebody cared about Rust and was speaking about Rust, it was like, yes. And I know MadeSafe was one of the earliest ones, and I thought, like, I don't know what MadeSafe is, but like, let me roll through it. You talk to me, and what do you need from us? But a really big production user, maybe the biggest, earliest Rust production users were Parity. And anybody here who knows the blockchain community, gotta know what Parity is. Parity is, well, I say you gotta know what Parity is, but I don't really understand what Parity is. It was a parallel in Rust, and now it's just kind of like a ton of people, and a ton of Rust programmers. Give me one moment. I just have to remember to touch my space bar voice all the time. So I was telling people confidently, like, there's definitely at least 16 blockchain companies using Rust. And, because you want that full screen.
No, I thought you hit the button to change the slide, but it didn't change the slide. So, never mind.
No, I'm just going very slow. This is kind of what I work when you get this and there's not a lot of slides here, but we're kind of probably falling behind. I was saying something. Oh my God, it's crazy. So just two, I was telling the conferences, like, you know, there are at least 16 companies in the blockchain domain using Rust. Isn't that amazing? And so last night I spent like 4 showering, like documentation pages I could, conferences, that Friends of Rust page, and now my list is 33. There are at least 33 companies in the blockchain industry that are using Rust for some purpose or another, and a lot of them, they're not all built literal blockchains. Some are super interested in Rust and are using Rust for things. So here's the boring slide to me, but when people keep telling me that we want to hear. Why do people like blockchain? Page that you is a application that needs like the utmost security. You write a memory safe in software, almost 100% of the can directly to some kind of that's a statistic people have told me anecdotally. Repeating that's true. In the blockchain community, you know, people also might plus those people are fighting. We see some like we do in every industry, but like Rust is a freaking safe bet. Like if you want to just make sure you got all your just use Rust. People are doing that. So it's interesting in the blockchain community for a couple of reasons. As I was mentioning before, for a long time we didn't know what domains Rust was useful for. If you like read the Rust website, you'll see them make all kinds of stuff this, does that. In particular, like people were saying, like web is WAS, big idea. And so this applies to that because Rust is not just consent or security algorithm. But Rust also turns out to be an amazing language for writing the scripts that run on a distributed computing platform. So it's different places. Is an amazing killer language for blockchain, and that's an advantage. Like EVM in also blockchain virtual machine theory, and it's very special, and it runs a special purpose language. And as with many trends in tech, that special purpose in the way, not smart contract platforms are just like incompatible with every one of them. Here, WASM. I'm not quite at the slide right. WASM, everybody knows WASM here. It's the thing that was created to create really fast web applications by running a very special sandbox virtual machine. And as soon as WASM started really getting to the point where it looked like it was going to happen, a bunch of blockchain projects were like, well, why are we taking the risk of building our own EVMs or our own virtual machines when some really smart people from the coalition of the biggest tech companies in the world already created a sandbox virtual machine that runs arbitrary code? So tons of blockchain projects that adopted WASM. And as happens, Rust is the very best. Right. So that was the slide I didn't care about. I still talked way too much about it. I care about blockchain industry is important for Rust success. And the reason why, okay, diversity is blockchain is kind of special in people and many entities. And a lot of ideas are like super crazy, but they're just really innovative stuff. And as I'm going to show you, 33 blockchain companies, they're not just on their own building, actually helping build the Rust community and the Rust ecosystem. There's all kinds of stuff they're feeding back up into Rust and making it better, not just from the community, but also and I'm going to really cool projects to show you. And I'm going to show you this many of them, but again, that I get at the end of the slide, this many of them. Go to towns and I look at the freaking stuff that the blockchain companies have given our community. So, of community, of code, the individual blockchain Rust communities. Crass, but from my perspective, my selfish perspective, that has come out of this explosion in blockchain activity around is the money. Okay, so I want to talk a little bit about like how Rust is funded and developed. Rust, you probably know, was originally, we say, sponsored by just to make sure it sounds like a big collaborative effort. But for Mozilla paid their entire Rust. But Mozilla's a tiny feeds off the teat of Google. We knew from the very beginning that like the only way for Rust to succeed is to build a huge coalition of companies that all are in Rust. And how to do that, but this kind of serendipity happened where this blockchain thing was crypto. All of a sudden, there were a whole bunch of people who loved Rust and had a whole bunch of money to throw around. I told you I was doing research. I looked through all of the past Rust conferences, 19 of them, and I sponsors of all the Rust conferences, and it turned out 16% of the sponsorship of all Rust conferences come from blockchain companies. I'm gonna be over you. I'm going to keep going over there because that's where my notes are. But, so, specifically, if I told you there are 33 that I know of, the super props. These are the companies that are putting their money out is money to bring community together for conferences all over the world. And in particular, I have to point out parity. Almost any time you go to them, you have a lot of pressure on parity if any of you guys are parity. You go to them and you say sponsor, they give you money, they'll show up, they'll let you. Amazing. They're one of the best years always out there trying to support us. And of course, everybody's on here has got their own self-interest because they want to recruit. But it's an amazing thing, asset to the Rust community. Really, everybody in the Rust. Stop it, Jane. She's pointing over here. Rust community cannot appreciate it. Okay, now we're going to get to the real meat of this, is where we talk about the cool stuff that the Rust blockchain can. There's even like a laser. We were talking probably tell that I've mostly been feeding this refreshment. Okay, so talk, and I'm just going to be gushing about a few of the cool projects that I hope you'll also be interested in some. No technical details, but a few of the speakers tonight are going to be talking about these projects, and they'll give you like deep stuff. But again, links at the end, go check them out, and I hope you will. So, again, the research tonight ended at like 1:30 a.m. when I decided I couldn't think straight anymore. I don't know. There's a lot of really cool that by necessity these blocks like that must have, and so they like that's because they have has one of the limitations. Tool in its production is written. If you're like me, I think like emulate BBM. Understand you can do um, recipe lines of 1,000 lines. All right, the next one you might know. You know, it's used to don't kill me. This is the other exactly analyze like exactly we have compute until I run out of compute units to whatever or we're just basically a really cool block. Stand implementation like etcd dev team. The team that's a bunch of so I have no idea if it's good stuff or bad stuff. Final VM last night. Interesting. They have just this has been around for special so we're looking at x86 and alright, with the next slide. And here's the next big area contributing to Rust. Tonight. Celebrities of Rust. But I really want to point the Dalek elliptical curve careful. Who are Western Navy, a very I knew they had they did that zero full of time evaluation all in Rust, which is like all kind of like the fundamental if you want to crazy secure crypto stuff. Because this kind of stuff. Alright. There's even more crypto. I saw Z independent pairing. I don't know what it is. Pairing crypto, which is not Z dash. Tendermint. Rust. I'm like this. Gotcha. But several things in Rust, including a really sophisticated digital management system and interface to UV. There's even more. I can't talk about it because I'm so out of time. Great. Okay. I put this slide on communities. I'm running out of time. I'm talking about these is super risky. I talked about hours. About about my ideas about communities, and he told me to shut up and don't say anything. But like, I just want to point out that like, I think everybody here probably knows about people generally take a lot of it's kind of sense, you know, sharing and give back to your brother and things like that. The Russian community takes a lot of pride in helping. And again, I'm not a blockchain expert. What I'm only here to tell, I'm going to say like blockchain communities don't have all. And I think that the Rust blockchain communities together, the Rust blockchain communities together, Rust blockchain community in general. Because one of the things I'm afraid of is that the Rust blockchain community is like, I told you, I just did all this research and stuff, and learned like a ton of stuff just by like 4 hours of reading that I didn't know before. And like, I follow Rust. And so I want to see more and more the Rust blockchain community is an important and appreciated and recognized part of the Rust community. And there's a lot we call U4, like three all together. And also, I handed it because I really like this picture that I found. This slide, I don't have a whole lot for it. This is like a mandatory slide where like I engage her and say like how you can help the thing. But this is also the slide where I ran out of time. Like, however long it was right now, so I don't have a lot to say. I want to draw a dichotomy about the Rust community and the Rust blockchain communities. And they can, the Rust blockchain community can help the Rust community can help the Rust blockchain community. The Rust communities can help the Rust community. And I want to say that blockchain companies, I find please what we're doing. We need so much help. Like, if you're part of the Rust community and you care about like you're interested in all of it, those silos of people with bad Rust habits, you know, they develop. Like, you can all share that knowledge and make each other better. When you see people doing things that I care about, but like are really cool and they're contributing, like, you know, support that. I want to support everybody who's using Rust and doing their best to use Rust. I want Rust to know how to help us succeed. Oh, also, I think a conference sponsor. Good Lord. Conference, all the things, you know, they're trying so hard. Let's go up and say, thanks for sponsoring the conference. They really appreciate it. Closing thoughts? I don't have started out with kind of weather. It would be useful for fire. It turned out it was useful for everything. Blockchain. Thank you. No questions, but I hope this was helpful.
You're wearing your nice fit green. How about your orange hoodie?
I'm a core developer at Nervos. We are building a new layer 1 blockchain solution. I believe we have some novel ideas, so if you want to learn more about Nervos CKB, please come to me. But unfortunately, this talk is not about CKB itself. This talk is focused on the CKB VM, the brand new VM layer we're building here. So today's first part is perspective. You can design a better VM for blockchains. The second part is the main. It is more aligned to our topic here. How we can build. We all love ROS. We all love writing ROS, but as we're going to show, writing ROS code, writing performance, you need to be careful about. The game is about how we can design a new version. Two parts is determinism. Same result when you run it and running out. VM instance same machine for blockchains. The second is security. Well, virtual machine should not it would be better if I just don't use the mic or something. Okay.
I'm going to turn the mic down.
Okay, okay. So security is the thing. We must ensure that the VM is secure at most. It shouldn't steal anything from your virtual machine. steal anything from your main computer. Your virtual machine should be safe. In virtual machine should also be safe. If your computer has other sensitive information, the VM should not be able to tamper that with. Also, the VM has to be able to enough. So when the run on the virtual machine, it can do it just as an execution. There's no other thing it should damage. But this thing only requires a blockchain VM. We also think make a blockchain machine better. We did a retrospective, we did some thoughts here. We believe there are three main properties. The first thing is that a blockchain virtual machine should be flexible enough to support any case. And yet it also should be simple enough to reduce the attack risk. We can have a complicated version that can solve any case, but a complicated one means more attack surface. More attack surface means it may not be secure enough, and it's also so hard to do a security audit to make sure our VM is secure enough. Also, the flexible part means that although we can mostly use hard forks or soft forks, kind of upgrades environment to upgrade them. One thing we should be sure is that the program, the smart contract you write today on the VM should also be tomorrow. It should be also validated that a year from now. I think it should actually be validated forever. This is only we can make sure that developers' efforts won't go in vain. So this is the first part. The second part is that we believe a blockchain virtual machine should have industry support. Although we can design a brand new virtual machine that runs everywhere, but the problem is that if everything you build start from, you have to write your own tool chain. Everything has to be built by your team. If there's no industry support, you're on your own. And it depends on how many resources you can. Good enough. The third part is that we should have a reasonable future growth model. We have a smart virtual machine. We must make sure that a smart contract should have certain amount, should be associated with certain amount of cost. If the contract does more work, it should cost more. If the virtual machine does less work, it should cost less. And this thing has to be future-proof because we don't know 10 years from now what CPU we will have, what computer architecture we will have, and what platform we should run this smart contract. What we cannot have is like this smart contract costs like 10 today, but costs only 5 like 10 years from now. That's going to bring catastrophic to our blockchain system. With those goals, we search, and we believe we found the answer in this. So RISC-V is an open and frozen instruction set architecture. It's originally designed by a bunch of by a group of professors. Their goal is like they want to revise what the computer architecture has advanced in the past 50 years, and they want to start from scratch and build a new instruction set for the next 50 years. So one question they ask is like, if we forget about all the burdens we have in the instruction and design something that works for the future and works better, how this thing is going to be? So the answer is RISC-V. So our CKB VM is actually a standard compliant RISC-V instruction set software implementation. We didn't introduce other variables. We just built a standard RISC-V compatible software CPU. And what I mentioned is that our goal is the three goals before. We didn't aim to look for a hardware-based instruction set. This is because we found properties in RISC-V. Let me show you. I think RISC-V is better. The first thing is that RISC-V has real industry support. We have all kinds of hardware companies building RISC-V CPUs. Western Digital has announced that all the hard drives in the future will be based on RISC-V. The main control chip in Western Digital will be converted to using the RISC-V instruction set. So I would say it's very likely in the next 10 years, any hard drive you buy from Western Digital will have a RISC-V CPU in it. Also, right now, if you have a latest NVIDIA GPU, it's very likely it includes a RISC-V chip on it. They usually build their control chip. And also there's a whole bunch of other companies, they're all building RISC-V CPUs, but this is only the hardware side of the world. On the software side of the world, RISC-V has been supported by upstream. It has also been supported by the GNU tool chain. So these things are all upstream, they are officially supported. If you put down GCC 9 and build it support, you should be able to write a C program and compile it to RISC-V. Recently, LVM also announced that starting from LVM 9, RISC-V is also going to be the official support instruction set. It means any RISC-V code in the future, any LVM standard distribution in the future will be able to generate. There's a recent by the group showing their progress in their RISC-V core. Soon we will running on RISC-V chip. The Go also has development in their work. As of now, already compiles programming to RISC-V by running on the RISC-V CPU. The same thing happens to Rust. Rust also has growing RISC-V for right now, but I think with time and soon Rust will run RISC chips. So here is that the software industry is really embracing RISC-V from hardware point of view. So besides industry support, RISC-V instruction set is very minimal. The complete core RISC-V instruction can fit to two single pages. And instead of the instruction here, you can see that each has an associated memory and the encoding formats. You can see this everything. That and actually, if you look at our CKVPN, we don't even need everything here. So I just mark out the part. We don't need to see that we have plenty of space. There's only very minimal thing we need to support to build a RISC-V CPU in RISC-V in VPN. The result is, if you look at CKVPN right now, we only need to implement like 103 instructions. This is smaller than the instruction in EVM. This is also smaller than the instructions in Bitcoin script. This is way smaller than the instructions that you have in an x86 CPU. But even though RISC-V is minimal, it's also flexible. What I tend to like is we're not embedding a virtual machine in our CKB blockchain. We're embedding a real minimal computer in our chain. Okay, so easy to you can do with Thomas Web. You can whatever exists as I'm going to show with CKVPN new use cases. The first use case is like this. Today you can see that most blockchains use SECP256P1 as the same verification algorithm. There's also new development in signature verification like Schnorr, like BLS. But the problem is today we have this different this verification algorithm. But what about 5 years from now? What about 10 years from now? New signature verifications came out. How easy is it going to be to support it? We also see Bitcoin teams effort just to support Schnorr signature verification chain. But what if Schnorr becomes something old? What if newer things than Schnorr comes out? So our solution here is that instead of embedding a signature verification algorithm in CKB, we just take the verification algorithm, compile that to RISC-V, and we just add a RISC-V code onto our chain. The result is we're not bound to any single verification algorithm. we're free to support anything you want. If you don't like our official support one, don't worry, you can just use Schnorr and deploy on CKB chain, then you can use Schnorr to do signature verification. It just means there's no need to wait for any complete compiles. If you want something, you can do it right now. There's no need to wait for the team or to persuade the official team to support anything. And also, the part of CKB is that your deploy contract is treated the same way as our official ones. Our official included signature is just there because we put it there. It doesn't have any special privilege. Our contract running on CKB, whether it's created by the official team or created by all the community members. One I keep making is that if your blockchain cannot support maybe by a customer, maybe really call it a program blockchain. It is not a programmer. The second use case is like, as we can see, as Ethereum grows, people have smart contract developers to move to eBusm. They're deprecating this whole solidity thing, but the thing is, we have all developers doing solidity today. We have a lot of smart contract apps reading solidity. Are these efforts paying? If you're working in KB, the answer is no, because that we take or we take implementation script VM. How the VM directly into RISC-V, then we deploy on CKB. The result is that you can just run all EVM co-written solidity or the Bitcoin on CKB. I think this may not be a very, but it helps us preserve legacy. It helps us preserve history we have. It prevents all the efforts we have spent in the existing blockchains. And it also helps make a more vibrant and diversified ecosystem because you are not bound by smart contract language. You're free to use your favorite one and anyone you want. That brings to a different use case. You see, all the existing smart contract languages are really designed specially for blockchains. But what if I want to use a purpose language? For example, it has a very rich NPM ecosystem. Uses NPM, or what if I want to just write a TypeScript, or even OCaml and compile to JavaScript? Turns out, CKB case, because we can do is that we take a JavaScript implementation, we compile that C-based implementation into RISC-V, then we deploy the binary on CKB. The result that JavaScript code can also be running on CKB. This has our we have real supporting this use. The result is that you don't have to live with something like assembly script or any crappy language. Real JavaScript identification, and you can use that one. And of course, one question might be raised is that if we have this on top of VM solution, the performance might be a little bit of a problem. But we believe that use case measure to see if performance is really a problem. Also, the other way to tackle this problem is that initially, really, the problem is that we have this JavaScript enabled. It's really a 0 versus 1 case. And then as more and more users of JavaScript thing, the community might develop better solutions to make this thing more performant. And this thing, as this thing grows, things will definitely get faster and faster. And it might not be standing in your way any longer. And the final use case, and the one that's most asked when we make the choice to use RISC WebAssembly. Let me first state my conclusion. I believe WebAssembly makes a lot of sense for the web, but it's a questionable choice for parts. The first part is existing WebAssembly have certain making very suitable blockchain VM. The second part is looking into the future. WebAssembly has something that make it a bad choice for a virtual machine, for a blockchain virtual machine. The first case is like to look at some curves. This curve is a heap problem. language. When we use C or C++ or Rust, they use this certain computer concept called heap. But the problem is that current implementation implements heap in a really poor way. The only way that you can deploy a chat VM is to declare it is to predefine a block of memory in your module. When you run a module, you have to control how much memory you want. In some cases, this is going to work, but in some cases, this might not work. And look at how everybody is doing assembly. What they do is that in Java, they create a array buffer. And they just pass the array buffer from JavaScript to WebAssembly, and then WebAssembly uses that array buffer. And when they need to grow the memory, they enlarge the buffer. This is if we're working for the web, how are we going to have an array buffer exposed to WebAssembly in the I personally believe this is going to be a huge security risk. The second problem is that look at the WebAssembly spec, it has a whole section about non-determinism. And they non-determinism in a very sensitive way that makes a lot of sense because they want to optimize for a very secure, very performance system. But the problem is that this non-determinism is going to bring problem for blockchain VM because we stated earlier that the blockchain VM must be deterministic in all cases. And means all the WebAssembly VM you use in the blockchain today might not fit with your WebAssembly because your VM has to be deterministic. But the official spec for WebAssembly it has certain non-determinism. It means that you're using is actually a modified WebAssembly. It's not the same WebAssembly. Actually, there's one more important thing here, so let me now. As WebAssembly gets implemented and tested with multiple languages and architectures, we may revisit some of the design. First point is not relevant, but if you see it on the official web, this is a code. I want to point out the second point. When different languages have different expectations, then it's unfortunate if WebAssembly measures penalize one's performance by enforcing determinism, when which that doesn't care about, but which another language may want. This is actually not an assumption. This is actually something that has been proved by fact. You see, if you look at the WebAssembly spec, WebAssembly today has garbage collection implementation. They have garbage collection feature proposed and implemented in some browsers. The problem is those garbage collectors are only tuned from one set of applications. When people want to use the garbage collection for a different set of applications, they really run into because the garbage collector won't fit their language model. This brings a huge problem of pouring assembly. There's a real blockchain team working on this problem. They spend a lot of effort to work around this issue. And a bigger problem is the WebAssembly team states that they revisit. If you think about WebAssembly, it's actually a software spec. All people need to make incompatible changes is just to make all the when they sit in the room and when all they all agree with each other, and just ship a new version of it, which includes incompatible changes. This is the browser because our browser are all evergreen browser that gets automatically updated. But what about your blockchain? An incompatible change in the WebAssembly spec. How are your blockchains going to support? Do you need a hardware to support this, or are you going to only support an older version of which deviates from a then WebAssembly version? This is current purpose. Let's look at the future features. If you look at the WebAssembly official site, they have a lot of features that's going to implement it next. Some of the notable ones in threads, and on a different slide, multiple value, this import export multiple modules. These are all planned and proposals have been written, and there are real browser vendors implementing it. And if you further, there's different proposals they're going to add to the WebAssembly spec. This is some of them, and there's more features, a lot of features. So that raises a question, is there going to be really an end version, or is there going to be a stop point that we won't add new features to WebAssembly? To me, I'm afraid the question is no. WebAssembly will always be growing because browsers is growing, our website is also growing. So it really makes sense for WebAssembly to keep growing because when you only have this thing in the browser and the browser can get automatically updated, WebAssembly can also get updated. But for blockchain VM, as I mentioned earlier, this is a different situation. When WebAssembly gets updated to include a new feature, I think for a blockchain VM. And here with RISC-V, we think we can provide a different solution. We can build a layer that translates your existing WebAssembly code directly into RISC-V. And since RISC-V is an instruction set designed for hardware, it's frozen and it won't change in the 50 years. We can be sure there will be real CPUs built using RISC-V and there's no way you can change them. So this way, if you see a new feature like garbage collection, you can change the implementation for the garbage collection together with a program, compile that into RISC-V binary and deploy on CPU. If there's a new version of the garbage collection, if there's a different feature you need, you can do the same. You only need contract. Stays the same. This way, you get all the new developments in the WebAssembly stack without affecting your blockchain implementation or without jeopardizing your security of your blockchain. We believe, so a lot of people see RISC-V versus WebAssembly as a competition. We don't believe this is a competition. We believe RISC-V is just one layer below WebAssembly that use RISC-V instruction set to implement WebAssembly programs. And as I mentioned earlier, we believe a good blockchain virtual machine should also have distant cost model. As it turns out, there's a very natural because every single instruction running in the CPU has an associated cost, which is called cycles. It's only determined by the instruction you write. So the same instruction spends the same cycle whenever it runs and wherever it runs. So we can just use that cycle directly as the runtime cost model for your program. These things make to scale and it's also future-proof because it's defined at the underlying CPU by a work. So if your program does more, it will naturally cost more cycles. If your program does less, it will be also consume less cycles. And the different thing is that since we are actually building on RISC-V, which is a real minimal computer, just assign a single memory space as the space in the world. Actually, in our current implementation, we set out the virtual machine memory limit as 4 megabytes. This memory space you can do what you want, but what you cannot do anything that's beyond this 4 megabyte memory space. It gives you a fixed bounded memory space, and you can be sure your virtual machine is only consume this amount of security. Also, there's a lucky accident. We didn't design for this, but this turns out to be a very interesting use case. We're working to make VM really fast. We are making to make sure that our standard can just use a software implementation, but it doesn't stop the problem. It doesn't stop the use case. You can use a real CPU as a virtual machine in CKB. For no use cases, this might not help a lot. If you think exchanges and benefit from a higher TPS. So for them, they can just use the separate RISC-V CPUs, which guarantees the security because it's an isolated part from the main CPU, but it also runs very fast because you have a native business here. So we believe that using RISC-V as a blockchain virtual machine is finding a hardware instruction set or finding a software instruction set. It's only about we need to find the right abstraction library for a blockchain VM. So that comes to the first part about building how do we design a blockchain VM that suits. The second part is about how we actually build this VM in real using Rust. First, there's some real numbers. We have devised a second benchmark code written in C. We compile it to native code, which means the XADC that can running on out there. We also compile the same program into RISC-V. We also program WebAssembly, and we have different runtime spent by the same program in different environments. See this slide, our C modes. It has an audio, it also has a fast JIT. For the internal, 55 times the runtime of a native. For the JIT, it's about 8, which is actually within the same audio as a native environment. For our use case, more than enough. And what I want to compare here is that if you look at assembly, it's also roughly the same level of roughly the same level as our RISC-V program. You see there's two modes for the web, for the weather. If you look at the creative implementation, it's the same level of speed in JIT mode. If you look at the LVM part, it might be slightly faster. But this gets more interesting. We had actually live implementation. As Brian mentioned earlier, our CKD event only about the common creative part of the WebAssembly about 100,000 lines of code. I don't know how many lines of code that LVM part to be. Although I know lines of code part of the thing, it might not contribute the big picture, but can tell you that we do very sophisticated compiler technology to VM fast. One more is that due to the non-determinism in web, you can use Weismer. You have to modify that part to eliminate those non-determinisms that may actually make this web as VM slow. Actually, one thing I keep complaining about is that allocates about marks to be a machine. But when they're in their blockchains, they take an old, slow, and crappy interpreter, which doesn't match the speed of the fastest VM. I think, but with CKD, the same implementation, both fast as the latest WebAssembly implementation, and secure enough to run in environment. Yeah, we're not the speed, the main factor contributing to the is about finding the right abstraction. With the abstraction, we don't need to do a lot of code. We don't need to optimize everything. Do a whole lot of different optimization or use sophisticated compiler technology to achieve the speed we have. And it helps us a lot in this case. For most of that's really maintainable and can maintain the code. But when we really need to extract every bit last bit moments, we can just go into C code. Even the this. As I mentioned earlier, in most Rust, but be aware there are certain parts that Rust also great. The first thing to find out is that we write this thing which is an enum, not an enum case, but this consumption for this thing grows really quick. The initial version to for a single instruction takes about 48 bytes. 48 bytes. A single RISC in its original encoding only takes 2 or 4 bytes. And put into the Rust takes about 48 bytes. This is going to put a lot of pressure on memories and cache errors. So what we have to do is that we turn a single enum thing into a 64-bit integer. We have to the data we want, a single byte of this 64-bit. This defeats the purpose of the beauty of the Rust enum type, but this honesty. The second part is that we all know that Rust has this amazing pattern matching feature. It really simplifies and help you maintain your code clarity. But the thing is, these things are not always so fast. So if you have an enum whose subtype each contain a different way. So what you actually want from this PD rule is that take a type of the app and then jump directly into the code to execute the different part. But what instead is done in the example is that it compares the value each 4 times. First time it compares if it's bar, second time compares if it's fast, third time compares if it's a different thing. So in the worst case, if your enum has 4 different subtypes, you really do 4 to see if it is a different type. This also contributes a lot of part in CKBBM in the original version. And if you solve all these things, there are certain parts in the Rust compiler which are obvious. On the left side is the thing that's using an old loop, which is like how you in C. On the right side, we have an iterator-based part, which is like that should be fast and help preserve code clarity, and which is written in the Rust way. But the reality is that the code on the right runs 3 times slower than the code on the right for a single change like this. So we have to revert the Rust way of doing and go back to the way of doing things. And at this stage, we have our Rust-based interpreter, but it's also slower than our standard. So we have to look elsewhere. So what we ended up is actually an open written by the creator. What is ideal is based like current C compilers and the compiler which does back then, but still here is that they only optimize for one type of layout. But if you're building a machine, you really want a different type of structures. And for this different type of structure, the current C compiler Rust won't help a lot. Really go a different way to really handwritten assembly-based interpreter to make sure this speed up. To show here, so this is what a Lua JIT needs to run a single add instruction. You do a little count here, we have about 13 instructions. So it takes in the assembly-based interpreter, it takes about 13 x86 instructions to add instructions. For comparison, a normal C-based interpreter usually need to take like hundreds or even thousands of x86 instructions to finish the same thing. So from a raw comparison, you can see that an assembly-based interpreter can really help you extract speed, performance you want, and make sure. And we basically do the same thing for CKBBM. So this is how CKBBM speeds single RISC-V add instruction. And also here we have 13 x86 for one RISC-V add instructions. So the ratio here is 13 versus 1 implementation, which is usually like 1,000. This brings us a huge speed up. But this actually is where I show the number about 50 times slower than the native version. But we didn't look at all the assembly here, only the 4 in the middle layer actually work. Everything else is just overhead. So is there a way we can eliminate all this overhead, only do the work we need? That's how our AOT. So how TG works is that we take the RISC-V program and we compile to x86 program. So in this, we just x86 assembly. It doesn't have to use any. There are certain extreme cases where the general carbon we have the VM that only contributes like 1 or even 0.5% of the time. And the good thing about Rust is Rust foreign interface that really helps a lot in our implementation. And we believe the best word to write a performant Rust program is actually a balance. So in 90%, 80% of your case, you have a Rust program which is written to high level maintainability and has a very good code clarity. We need to push the last bit of performance out there and can go directly into a C layer or Z layer to help you achieve that. This is the stack gathered from our current program. You can see that our project has like 5,000 run lines of 1,000 lines of C code, and also 1,000 lines of code. That's all you need to build something as performant and as complete as CKBVM. So as a compiler, only apply certain technologies, but we don't use like sophisticated technology like the LVM case. With the right abstraction, we can achieve the same amount of performance there. So I believe that software here is mostly about abstraction. And for blockchain VM, we believe this file is the perfect software. And that concludes my question here, but I will stay here back afterwards.
Always bring some discussion about web. You can talk to him. Let's start the next one. Sorry. He's from new protocol, and he gives some talks about model checking and smart contract. And this time he gave us a talk about Rust smart contract APIs. Thank you.
Thank you. That's wrong slides. Nope. That's wrong slides. Where do you have my slides?
Okay.
That's not mine. Okay. So my name is Max. I'm going to be talking about Rust smart contract APIs from the Near protocol blockchain. So I'm not going to give you much of the introduction of what blockchain is and WASM is, so let's just jump right into the architecture. For most of the blockchains, the high-level architecture of the node is that you have a blockchain layer, you have runtime layer. Blockchain layer does stuff like network consensus, storing the blocks. It also exposes some RPC APIs, so it can act as a microservice. Runtime layer is what we're going to be focusing on today. And it has virtual machine for running your smart contract. And it has the smart contract code, and it also has a state storage. State storage is basically where you save the side effects of running the code in a virtual machine. There are basically two camps these days in the blockchain world. One of them is like, let's use a general purpose virtual machine like WASM. Well, today we also learned about RISC-V. And the general purpose language or like Rust or TypeScript. And another camp is like, no, let's write specialized virtual machines specifically for our blockchain and use specialized language. So there are obviously pros and cons in these two approaches. With WASM you have existing tooling, community, and it kind of passed the validation check by the community, meaning if the language existed for long enough, it's a good language, the features are polished also, right? It's also general purpose, means it's, you can write almost anything. Turing complete, can be viewed both as pros and cons. the specialized virtual machine, usually they fine-tune it to a specific blockchain. And in some cases, if it's like a functional language or non-Turing complete language, it allows formal verification, which is good. The problem is it's a niche language. Not many people know how to write in this language. And yeah, so our blockchain is in the WASM camp because we believe that WASM checks out all the checkboxes of being a good virtual machine for the blockchain. It was designed to be platform independent, check. Determinism, just don't use floats and you're good. Sandbox execution compilation, well obviously, I mean, you're going to be using LVM and crane lift, you're going to have bombs, so there are actual compilers there that are single pass compilers. They don't have bombs, and their code base is actually really small. One of them is written by Parity. It's called a Lightbeam, really good, fast compiler. And they have, the actual benchmarks matter a lot, you know. Like every company has their own benchmarks according to some benchmarks, like Ethereum has their benchmarks of WASM, the overhead of running Rust compiled into WASM over the native, according to their benchmarks, is like 80%. So it's like plus 80%, 1.8 multiplier there. Small size of the compiled code, that was what WASM was designed for. You know, you open the web page in a browser, WASM is getting sent over the network. Was optimized for the small compiled code size, and also close to machine code, which is good. Runs pretty fast. If you write smart contracts in Rust and compile them on the WASM, then you have some bonus features. Two of them I talked already about. It's existing tool and community, code transfer. Also you have memory safety with Rust. But also another one is zero cost abstractions. So to remind you, zero cost abstractions is like if you don't use feature, you don't pay for it. And even if you use feature, you couldn't have hard-coded it, like hand-coded it better yourself. And Rust prides itself of being very zero-cost abstraction-oriented language. So it has these iterators, futures, like CERDE, supposed to be all zero-cost abstractions. And like if you find some issue with iterators, like it 3x slower than a handwritten for loop, you should actually file a bug. So yeah, it's really good for the smart contracts because we want them to be small and efficient. So if you import the iterators from STD, it's almost as good as writing for loop yourself. There are existing blockchains out there that support smart contracts written in Rust. I have listed some of them. If I missed you, raise a hand. So the first one is our blockchain, Near Protocol. We have Rust API, which we call Near Bindgen, for the lack of originality. Then we have Perlin. They have their blockchain called Wavelet. And also they call the Rust API just smart contract. Then we have eWASM. That's a really great team. They have created API not just for Ethereum, but for Ethereum-like blockchains, because they think there are going to be many of those. And Parity created Ink, which is not just Rust API, but also standard library for their Substrate Polkadot blockchain. And then Oasis, they have created Mantle. Nick here, I think in the audience, maybe he's gone already. He wrote Mantle. And then there is deprecated PWASM, which is Parity WASM plus Fleetwood, which is like a standard library for smart contracts. It was written for Core 1 blockchain, which was the first blockchain to run WASM deprecated. So this is like a high-level architecture, which is similar for Rust APIs. You have WASM executor running Rust contract, and then it communicates with the blockchain layer, state storage, which I moved here separately through the contract interface and blockchain interface. So contract interface are basically exports of your smart contract, like what the functions that your contract exposes so that blockchain can call it, like deploy, you know, deploy function is quite common. Then a blockchain interface are functions that blockchain allows the smart contract to call, like what is the current block index? What is the amount of money on the given account? What is the account ID? And here I kind of separated it into state storage and everything else. And we'll see why later. So here's an example of smart contract written in Ink. Ink is the EDSL, embedded domain-specific language, which means you can write a smart contract in Rust, but you have to follow certain rules. Like you need to have certain structure, you need to call certain macros. So this is the example of smart contract that we're going to use throughout different APIs. It's incrementer. What it does, it just increments the value. It has like one value there, U32, and one function, increment. You call it, it increments the value by the given amount. It also logs it. So the contract interface here is a deploy function. That's what blockchain is going to call on the contract. Also, when you wrap it with this macro contract, then it's actually going to generate some functions that you don't see right now too. So it's also the part of the contract interface. The blockchain interface is what you can call on the blockchain. Like for instance, env print line. That's like a login function. That's how they expose blockchain interface. And then another part of the blockchain interface, the state part of it, is basically if you want something to be preserved as a state on the blockchain, wrap it with storage value, for instance. And then this value thing, it's like after you call this contract one time, next time it's actually going to be preserved. So that's the state part of the blockchain interface there. Unfortunately, it only works for some primitive types for now. So mental EDSL looks like this. You have different macro there, derive macro, service. Then you pass an additional argument called context in each function that you want to be exposed as the smart contract function. And then instead of deploy, you have new. And then you also need to declare your own function main here. And you need to decorate with indexed the stuff that you want to be, I think, on the blockchain. And also you need a compiler plugin to actually compile it into WASM. So our thing, if we take the same contract in our Rust API, it's going to look like this. You just decorate it near bindgen. You need to derive default serialize, deserialize. You compile it. It runs on our blockchain. Behind the scenes, we're going to derive a whole bunch of code for you. Actually, our smart contracts, we not only allow Rust, we also allow TypeScript and Ethereum. So we want them to interop with each other. And they understand JSON. So what we're going to do behind the scenes is we're actually going to serialize, deserialize arguments and return values of your functions into JSON. See, but you're not going to see this because it's all hidden behind this procedural macro. We also have context similar to Oasis blockchain. And the state, we're just going to derive it for you. You're not going to see what we do there. But if you want like a fine-grained control, you can have it. Yeah, basically this slide explains what I just explained for you. Our special macro iterates over the functions. It looks at whether it's mutable, not mutable. It understands whether the state should be saved or not. Default, you can have your own deployment initialization function there if you want. There are other blockchain from Perlin that does pretty much the same, except arguments. They are not. You have to pass them through the structure called parameters, and then unpack them manually. So the big question is, can we unify all of them? Oh, because they kind of look similar, right? So contract interface, yes. Straightforward, you have just some procedural macro that generates all the stuff for you, right? You need deploy, sure, you have a macro for deploy function, new, like you can generate all of them. With procedural macros, users do not even need to know that they expose some functions for the blockchain to, then the blockchain interface, that's the big question. And that's basically going to be the core question of this talk. And to answer this question, which we're going to answer at the very end, we need to go back in the history because we're going to learn from some mistakes that we've done in the past. And brief history of WebAssembly. It all started with mscripting. So there were some guys that were like, let's compile C++ and JavaScript for whatever reason. And they did it by introducing some hacks that were basically like annotations in JavaScript. It's a valid JavaScript that were emulating the type system, right? Then SpiderMonkey team from Mozilla noticed it, and they thought we can actually utilize those hacked annotation to run our engine more efficiently. So they did more annotations, and that created Awesome.js. And then what happens is when SpiderMonkey engine notices that it's an Awesome.js and not just plain JavaScript, it switches to a completely different mode and executes efficiently. And it was so efficient that they were able to port Unreal Engine and like MySQL and all other kind of large programs to Awesome.js and like run it efficiently in a browser. It was huge success. Everyone noticed it. large companies and organizations, especially those behind major browsers, noticed it, and the momentum of this success allowed them to get together and create a new standard better than ASM.js, which is WebAssembly. And the Emscripten then also allowed to produce not just ASM.js, but if you want, you can compile it C++ into WASM plus some JavaScript glue code. So that's how you would run some program compiled into WASM with Emscripten in the browsers. You have some WebAssembly module, and then inside the same WebAssembly module that you compile, you have some glue code. Because what happens is that if your C++ program accesses libc, and it like does the file read, this gets translated to the special ugly function called syscall3. And it is ugly because you have this which, you have two arguments here, which and var args, and var args is basically a blob of serialized arguments. So, not nice. And then JavaScript glue code wraps it all, exposes this syscall, and then unpacks them, and then knows what to do with them, like, for instance, it does some local storage on the browser operations. So the big question is, like, how do we run it outside the browser? Because people wanted to do this. So they had some runtimes for WebAssembly. But now WebAssembly runtimes that will run in this WASM code that you would generate previously with the Emscripten would have to emulate this glue code, the JavaScript glue code. They would have to expose the same functions here. And that was pretty bad, because now you have glue code there, emulation of the glue code there, so it's emulation of the emulation of POSIX. This thing is not strongly typed. This whole thing is not nice. And yeah, this is bad. This is like bad for two reasons. Two types of glue code there. Also no specialized interfaces. It's really hard to access DOM. And other things if you want to run it outside the browser. And so there came WASM system interface, WASI. And this is a very fresh effort that was announced early this year. Basically, the idea is, let's standardize all these imports that we had, but instead of ugly syscall3, we're going to have something nice looking that looks very much like libc. And we're going to have different modules for different tasks. Like core is basically going to mirror POSIX entirely, except processes. Processes are going to be outside because some systems just do not have processes, even if though they support POSIX. Then crypto and sensors and 3D graphics and even smart contracts were envisioned as separate modules in this WASI. So now if you write WebAssembly module in WASI and you like try to read from a file, like here, you call this nice function, and then the WASI enabled WASM runtime will expose this function. That's it. Very nice, no glue code. However, some people still did not like it. There is a nice post by Ben Laurie, who is a security director from Google, with the title, How to Ruin a Perfectly Good Container, which is a critique of WASI. Well, it's mostly a critique of POSIX and the fact that many people continue emulating POSIX on systems where they actually don't need to emulate POSIX. And he criticizes POSIX. He says, like, POSIX was invented in the 60s, and the use case was completely different. There was a mainframe where multiple people would work on the same mainframe, and those people were all experts, and they would only run really simple programs that were easy to understand. So you know what the program was doing because it was simple. You just didn't trust people. So the threat model was different. We had untrusted tenants on your machine, but trusted software because it was so simple and so small. But these days, the threat model is different. The software is so humongous, you cannot understand what it is doing. If you want to somehow constrain it, you basically need to do it on a different level. But people are trusted because realistically, in most cases, the people who run code are those people who own the computer. I mean, in most cases, there is one user on the machine. And they're actually not sophisticated enough to read the source code, even if they were able to read hundreds of thousands of lines of code and understand what the hell it is doing. And the union of the protection now also changed. Previously it was files. You just constrain users to their home directories. Now we want it to be higher level and more like fine-grained data items, like entries in your contact list, keys in a keychain, like other things like that. So he argues that POSIX is not suitable for that. And he says that many containers go through this life cycle. First, they see that POSIX is like opens too many things. It's really hard to control. With POSIX, if you can only have like either full access to the network or no access to the network, there is no fine-grained control. And so they put it in the container because they do not understand the code that runs in there, but they want to somehow constrain it. And then they're like, oh no, the old code doesn't run on this container. Like WebAssembly, we did not expose the file system. Let's emulate POSIX inside. So they emulate POSIX inside, and we're kind of back to square here. So there are some issues with POSIX that I already told you about, like either full or no network access. People want to run stuff on IT devices. Some of them don't have file systems. This file system-based security, in some cases, can be cheated, not abstract enough. So POSIX is an old standard. So what happened with WASI? I'm not sure because of this feedback or for whatever other reason, is that they took this WASI core module, which was a mirror in POSIX, and they split it into multiple modules. Like, well, not split, they're gonna do this, it's a future effort. Like file system gonna be extracted, random numbers and clocks. So the idea is to have human readable, simple, small APIs in each of the WASI modules, so that when user runs a program, they can understand that what they're granting as a permission to the program. Right, what about blockchain and WASI? Can we use WASI as a standard for the blockchain smart contracts? This is the world of the Rust smart contracts in a blockchain these days. And there's basically blockchains that do not emulate POSIX and do not just have some their custom imports, do not try to fit into WASI. There is one blockchain that is trying to fit into POSIX and WASI. This is the Oasis. They are trying to emulate POSIX by being like, if you call inside smart contract like environment variable named block index, you're getting block index. So they basically access the blockchain interface through the environment variables. When they try to do cross-contract calls, they actually open the socket. And what happens is that inside this gets translated into actually not opening the socket, but like actually doing a smart contract call. So they emulate in POSIX, at least they're going to, with WASI core, which is going to be split. So the problems with this emulating POSIX inside smart contract is that if you want to do some very simple thing, like let's save hash map onto the blockchain, you have to save it on a file. So you need to somehow either serialize it or have some format of saving into the file. And then inside the runtime that runs your smart contract and that exposes you a fake file system, it needs to reinterpret it and put it on the Merkleized tree, because most of the blockchains are using Merkleized trees or kind of hashed trees for their state storage. So the problem with that, now we have again glue code here and there, just like with mscripting. We have glue code where we save structures that align perfectly with the Merkleized trees, but we save them into files, and then we have emulation of the glue code where we try to fit file system onto the Merkleized tree. So that's bad. Two types of the glue code. Portability is broken again, by the way, but now not because of the IoT devices, but because some blockchains might actually be stateless. As it turns out, Ethereum is seriously considering to have a stateless smart contracts in 2.0. I'm not sure how it's going to work. Maybe they're just going to save the result of the execution, but not the state. So the big question is, what happens to smart contracts that use file system and try execute on like Ethereum 2.0? Yes, so that's the problems with emulating POSIX on WASI. But the big other question is, can we use WASI at all? Can we have a general common standard, common denominator among all the imports that blockchains expose to Rust smart contracts? So just let's go through those imports that blockchain exposed to the smart contracts. So this is our NEAR protocol. It's like about 30 imports. About like a dozen of them are related to storage and iterating, like walking on the Merkleized tree because we want to utilize the properties of Merkleized tree and not just use it as the key-value storage. Then a whole bunch of them are related to our synchronous cross-contract calls because we do them asynchronously and not synchronously because we're sharded blockchain, and it's really hard to do synchronous calls with sharded blockchain. And a bunch of them are related to like economics, hashing, and other things. This is the int from parity. They have synchronous calls because I think they happen only inside the dot of their polka dots. And the storage only exposes two functions. It works only like key value storage. Save key and value and get value by the key. Perlin goes a bit lower level. They work more with the blobs of data here. When you say send transaction, you pass the payload, and payload is a blob of data. And when you get the payload, you get the blob of data too. So they operate with blobs of data there. Ethereum 2.0 has two types of the API. There's low level and high level, at least in the plan. So low level API is what they use for what they call execution environment. So Ethereum 2.0, they have execution environment, which is just an additional layer of virtualization. It's like WASM, and then on the top of it, they can run either EVM or WASM or some other stuff. So they have two layers of virtualization there. And for that, they need a low-level API, which operates with blobs of data, because they don't know what the virtual machine is going to be running on top. So they just like pass it the blob of data. There are just 5 functions. And they have high-level API. Supposedly, I think for the WASM running inside the execution environment. So this is like the second layer of virtualization. It's like 33 of them. And they're very Ethereum specific. So the only thing that you can notice here, like common denominators, is some financial stuff like get my balance, which is also a very different variable for everyone. Some people use 128, some like I64. But also key value storage. That's what was repeated many times. So maybe we can extract key value storage and also cross-contract calls. But cross-contract calls are difficult because everyone has different take of cross-contract calls. So the idea of how we can unify it is that let's not push it. Let's keep our imports to ourselves, like everyone has different imports. And as we converge to the common denominator, we take things that seem to be common and extract them in WASI modules and start using those. So you saw this context and env kind of variables available in smart contract APIs. We just move some stuff from them into the WASI module. For instance, key value storage is the great candidate for moving out from into the WASI module. And as the time goes, we're going to be extracting more and more stuff and becoming more WASI-like, and maybe at some time in the future we're going to converge. So that's the solution. Start with extracting key value storage, wait some time more, maybe we're going to find more common denominators, and second step is unknown. That's the end of my talk. This is our team. We have 14 people, a bunch of them from Google, Facebook, some MemSQL. All kind of champions, medalists, and finalists of Top Coder, ICPC, and other competitions. These are our links. Questions?
Smart contract things, just catch in.
All right, thank you.
Thank you. Thanks a lot. Thanks for your patience, and we are honored to have Tony to join us finally. We're so happy to have you here. And Tony is a co-founder of how to spell that? Christian, okay, sorry. And he's a cryptography and infrastructure engineer, and let him to introduce more about that. Thank you, and thanks everyone.
All right. All right, hi everybody. I'm Tony Arceri. Tonight I'm going to talk about Tendermint KMS and Abscissa, our Rust application framework. This is kind of a crazy day to me with Congress asking about like the software supply chain of nightly Rust and blockchains, and here I am talking about Rust and blockchain. So yeah, I'm Tony Arceri. I've been doing Rust for about 5 years. I've been doing blockchain stuff full-time for about 3 years. I'm co-founder of Occlusion. We are a proof-of-stake validator company. So we host infrastructure for proof-of-stake blockchains, also developing a lot of stuff with Rust in-house. We primarily focus on Tendermint, but we're going to validate a lot of networks, including we're very interested in Solana, for example. So today's talk, I'm going to talk very briefly about 4 different things. First one is the Tendermint key management system. So this is a key storage solution we built specific to Tendermint. So it's kind of blockchain network aware. But in the course of building it, we built a few generally useful libraries. Some of them Brian already mentioned. So one is Signatory. Signatory is a general purpose multi-provider digital signature library for Rust. So it's kind of an abstraction for doing digital signatures. We also made ubhsm.rs. So we implemented effectively the SDK for these inexpensive ubhsms from Ubico from scratch in Rust, and I think made possibly the only, or at least the most mature HSM client that's available in Rust today. And finally, I'm going to talk about Abscissa, which is our security-oriented Rust application framework. So let's talk about Tendermint KMS. So it's a key management system. It's on GitHub. There's the URL at the bottom. But to start with, let me just talk about what Tendermint is. So at its core, Tendermint is a BFT protocol. So who here has heard of Raft? Consensus algorithm. So Raft, the core idea of Raft was taking this older protocol, Paxos, and combining some of the operations within it to simplify them to use a single operation to do many things. So Tendermint is the same idea, but instead of starting with Paxos, it started with PBFT, practical Byzantine fault tolerance, and it applies a similar simplification. So it is also, in Tendermint also describes an implementation of this algorithm in Go. So it's designed specifically for proof-of-stake blockchains. So the idea is you have several of these validators slash block producers. One of them is picked via a round-robin protocol to produce a block. The validators all validate that block through this sort of like pre-commit multi-round protocol. And then they sign each of these blocks if they think they're valid with a 25519. So you do this 2-stage protocol, pre-vote, pre-commit, and at each stage they sign the blocks they think are valid and should be the next block. So Tendermint also has this thing called the application blockchain interface. So where most blockchains are tied to a specific virtual machine like the EVM or the 2 we heard about tonight, Tendermint is kind of agnostic to that. So you can just plug in whichever consensus engine you want. That's called your application. There's still this notion of transactions, but transactions to Tendermint are opaque and application specific. So you can plug in WASM or what have you. The idea being that Tendermint, it can unite all of these different blockchain networks together through this protocol called IBC, the Inter-Blockchain Communication Protocol. And probably one of the most notable things about it is some of the only production proof-of-stake networks are based on Tendermint. So the core one is Cosmos Hub, but then there's also the Iris network and Terra. Iris is basically the Chinese equivalent of Cosmos Hub, and Terra is a Chinese stablecoin. So these are all production networks running on Tendermint. So what is Tendermint KMS? So the core idea was we wanted a secure key storage solution for validators, and we didn't want just one supported HSM, so it supports both UBHSM2s and ledgers, along with software back keys are also an option, although I certainly prefer HSMs for this purpose. So another thing we wanted, because Tendermint lets you run several of these networks, they each have their own consensus. The idea was to have a central signing service, so every time you spin up one of these new networks, you don't have to deploy new hardware and new HSMs, and you can kind of share these HSMs among multiple of these networks. Some of its key functions is double signing. So BFT algorithms depend critically on the ability to make sure that the validators are not signing two different blocks. This attack has a few different names. There's duplicity or equivocation. Tendermint specifically punishes validators who double sign. In fact, there was a big double signing event on Terra recently. So if you double sign, your MAG goes poof. You get slashed is the term. So one of the Terra validators got slashed about the equivalent of $1 million for double signing recently. So it's critically important that you don't double sign. And finally, Tendermint KMS is running in production on several validators. So this is a production Rust application, and yeah, it's pretty much all pure Rust. Some of the only C code in it is libusb to talk to the UBHSMs. You can find it on GitHub under Tendermint/KMS, and all the other projects I'm going to talk about can all also be found on GitHub. So let's talk about Signatory. So Signatory is the signing abstraction library I was talking about earlier. So it presently supports ECDSA and ED 255.19. So we've support ECDSA over two different elliptic curves. There's the more traditional NSA created NISP 256 elliptic curve, and also SecP 256K1, which is kind of ubiquitous throughout cryptocurrency applications. ED 255.19 is this cool new kind of up and coming elliptic curve that's being widely adopted for lots of different applications. So Signatory supports both. It has a type-safe implementation of especially ECDSA. It's generic over curves. It's using generic array and type num right now, but it's really been designed with the goal of supporting features like const generics to have type-safe bindings to ECDSA. There are providers for several popular Rust libraries. So ED 255.19 Dalek that Brian talked about earlier is one of my favorite Rust libraries in general. I think the world's fastest implementation of ED 255.19. Ring is another very mature and popular library for doing Rust cryptography. So I was talking about using that NISP 256 curve for ECDSA. It supports that. It doesn't support SecP, so maybe less interesting for cryptocurrency applications. Some of the other providers is Blockstream created libsecp 256K1, which is probably the most mature library for that purpose. So there is a ECDSA provider for that. And finally, it supports sodium oxide as a alternative ED 255.19 library. But what is one of the most notable thing about it is it uses a common set of traits regardless of whether you're using one of these software implementations or whether you're using an HSM. So I think this has classically been a mistake in a lot of these sort of like multi-provider abstractions in other languages. They make two different APIs, one for software and one for hardware. There's like PKCS11 is the big traditional one. So the problem is everybody writes to the software APIs, and then you can't just easily plug in an HSM to any library that uses this. So Signatory has been explicitly designed so there's one API regardless of whether you're using a software or hardware backend. It just kind of abstracts over that. So right now there's 2 HSMs supported, UBHSMs. I'll talk about that next. And then ledgers, but unfortunately our ledger support is only for Tendermint right now. We do plan on adding more HSM backends, like we would love to support keychain services on Macs, so you can do Touch ID and that kind of thing. So next, let me talk about UBHSM RS. So UBHSMs, you can kind of see it there in Ferris's hand. It's like this little tiny YubiKey size token. It does all sorts of cryptography. They cost about $650, so that's much cheaper than a FIPS HSM, which will run you north of $10,000 or more. So this is also under Tendermint on GitHub, UBHSM-RS. So really quickly going over its features. So it's pure Rust. So I started originally in CoreOS, had tried to write C bindings to Yubico's SDK, which at the time is closed source. And there's just so much, I contributed a few things to that implementation, but there's so much unsafe code there. I'm like, this is crazy. So then it turned out it's actually just basically using industry standard protocols. So I ended up re-implementing all of these in Rust, writing it on top of the libUSB crate, and we get a crate completely free of unsafe code that can talk the protocol natively. So most of the functionality in the UBHSM is available through this library. So I mentioned ECDSA and ED 25519 as signature algorithms, but it does a whole lot more, so you can export and import encrypted backups of keys. You can also encrypt arbitrary data. It also supports HMAC. It also has some pretty cool audit log functionality where it keeps an almost blockchain-esque like hash-based log of every single thing it does. So you can keep an eye on what people are doing with your UBHSMs. And then finally, as part of developing Tendermint KMS, testing is really hard with HSMs, especially if you want to do things like CI, where you're using like a hardware device, and CI is pretty impractical. So it contains a partial software re-implementation that behaves mostly like the UBHSM that you can use for testing and CI and all that sort of stuff. All right, moving on, let me talk about Abscissa. So in the course of developing the many Rust applications we have at Occlusion, we end up creating this sort of like copy-paste boilerplate we would use to spin up an application. And after doing this so many times, we did the hard work of kind of ripping that all out and making it into a library with an application generator. So quickly, so what is an Abscissa? Abscissa describes the elevation over the x-axis. So kind of the pun here is like, Abscissa gets your application off the ground. It's kind of a double pun here. So it's also named after this thing. This is a statue called Kryptos, found at CIA headquarters. It's still unsolved. Well, there are 4 panels, 3 of them are solved, the 4th one is not. Abscissa is the key to the K2 panel, the 2nd panel. So it used a thing called a visionaire cipher, which you should not use visionaire ciphers unless you're making cryptography puzzles. But that's what it decrypted to. And in case you're curious what occlusion is, occlusion was part of the solution to the Kryptos K1 panel. So it's kind of you know, a reference to this statue. So what does Abscissa actually provide you? Well, it's a bunch of things. We developed it both for command line applications and for network services. So it's pretty general purpose. So we've written several utilities. We have like a file archiver utility called Seer that does encrypted zip-esque sort of things. I'll talk a few more about a few more of the things it's used in. So one of our biggest goals has been eliminating as many dependencies as we can. So it comes with about 30 runtime create dependencies right now, which sounds like a lot, but when you look at things like request, the HTTP library using like 150, we've really tried to get that down as much as possible while providing a lot of functionality. And we think Abscissa, since we're taking this sort of like heavily security-oriented focus, we think it's particularly interesting for people writing blockchain applications in Rust. So really quickly, here's what's using it. Tendermint KMS, I already mentioned. I also work on the secure code working group for Rust. And one of those projects is RustSec. We have this utility called Cargo Audit, which will audit your Rust application for crate dependencies that have vulnerabilities that have been logged to our vulnerability database. So that's using Abscissa as of a few days ago. There's also, Parity that was mentioned earlier developed a open source Rust implementation of a Zcash node. So this is Zebra. So they did that in collaboration with the Zcash Foundation. So Zebra is now using Abscissa, and we have several internal tools we are in the process of open sourcing and will eventually do announcements about. I mentioned one of those is Seer, or file archiver. We also have a deployment utility called Canister, kind of oriented towards Amazon Firecracker, which is a very new, interesting VM from Amazon. So what functionality does Abscissa give you? So command line option parsing. So you may have used clap for this. We use this other crate called Gumdrop, simply because clap has a lot of overlap with the stuff Abscissa does. And it has a lot of dependencies too. So it's kind of like a lot of duplication of functionality. So Gumdrop has no dependencies and is great to use as a library. And it was written from the ground up to kind of be a proc macro DSL for argument parsing. So another thing it has is components. Did anybody see the RustConf 2018 closing keynote on entity component systems? So Abscissa is not an ECS, but we've taken some of the ideas from that talk and used them to build kind of reusable functionality you can share across applications. So there are two components built into Abscissa itself. One handles terminal interactions, so kind of colored terminal output, and the other handles logging. So far, there aren't any other open source components. We have a few internal ones that do things like key management and that kind of thing, which we eventually want to open source. I guess the other thing components do is figure out ordering. So all our logging goes through the terminal. So there is this cool sort of partial ord-based thing that looks at all the components, kind of like a dependency injection framework, figures out the order they need to start up in, and then starts them up in the correct order so they can go talk to the other components and use the ones they depend on when the application boots. So configuration files, so it has a nice simple way to figure out where your configuration file is, parses it using Serde, and then it also provides the ability to override things in the configuration using command line arguments, and it supports hot reloads of the config, if that's something you're interested in doing. So it's error handling. So it contains a generic error type based on the failure crate. So this handles things like causes, backtraces, and eventually we will want to hook it into things like exception reporters and that kind of thing. So as I mentioned, it's logging. So it uses the log crate as a facade, but it has its own log driver implemented as a component that logs through the terminal crate. Is kind of intended for things like systemd, journald, or Docker logs, or however you want to collect logs through standard output. So it's got secrets management. So one of our other in-house crates is called secrecy, and it talks to another one of our crates called Zero Eyes. Really the main thing it does is try to prevent secrets from being exposed. So this is really good if you have secrets in things you're deserializing with Serde. So it prevents them from getting logged by debug, and then it tries to wipe them out of memory when you're done. And then finally, as I also mentioned, there is this component for doing terminal interactions and color terminal output. So one of the things I developed it for was Cargo Audit, which kind of mimics Cargo. So if you want to make a Cargo plugin or something that outputs colored output that looks exactly like Cargo, it's all built in and ready to go. So if you want to try it out, the main thing you want to do is Cargo install Abscissa. And then this will install a little command line utility that contains a application boilerplate generator. So you do Abscissa new and give it an app name, and much like Cargo new, it will spit out this entire app skeleton that's ready to go. So it includes all of these little pieces, and it includes acceptance tests. It has its own built-in acceptance testing framework you can use to test your command line application. So I'm not going to do a deep dive into how it all works in this talk. You're not going to see any code. I'm basically done at this point. But if you're interested in that, we will have a blog post up tomorrow that does a big deep dive into this, kind of what the different parts of an Abscissa application are, how they work, and what the generated boilerplate looks like. So that's all I've got. Here's some links, and if I have time, I can take questions. If not, come find me, and I'll try to answer them.
Okay, and that's all for today. Thanks for everyone to coming, and we have Brian hiding there, and Shaw here, and Maxim there, and Tony here. So feel free to talk to them later on. We still have a lot of drinks at the door. So enjoy your time, hang out with all the speakers here. And thanks, everyone. And don't forget to check wrestlingblockchain.org and check the updates. Oh, and we still have ongoing events planning in San Francisco and Berlin and in China. Just everyone have any ideas, please let me know. Thank you.